let me show you the method of annihilators. Now that you have a sense of, you know, how we solve constant. So any constant coefficient differential equation can be expressed as a polynomial in the differentiation operator.
Yeah.
And since you can factor the polynomial into repeated reals or repeated complex factors that come in conjugate pairs, you can read off the solution set from looking at the kernels of those respective operators. So the method of annihilators kind of takes advantage of that. So what is the method of annihilators? Let me show you. So here's an example. Y prime prime plus, let's say, y equal to, oh, I don't know, e to the t. All right, so how do you want to solve this? So in your course, you write down the homogeneous solution, and then you look
add the particular solution.
You look for particular, and how do you form the particular solution? You
is it a guess and check type deal?
Yep, guess and check. So you go, oh, look at it, you go, oh, e to the t, so yp equals a e to the t.
Yeah.
Right. Okay. So here's how the method of annihilator solves this problem. You go, and it's really not disconnected from what we just talked about, but here we go, d squared plus 1 times y equals e to the t, right?
Yeah.
So this is, of course, a non-homogeneous equation. So how can you convert this into a homogeneous equation? Act by the annihilator, which in this case is d minus 1, since that on e to the t is 0. So we have d minus 1 times d squared plus 1, y equals to 0. Because when I get d minus 1 on e to the t, I get 0. Right? But now I have a third order homogeneous equation, and I can write down the solution to that from the general technique we talked about before I hit the off button. So I get y is like c1 e to the t plus c2 cosine t plus c3 sine t. Or of course I'm taking the real and imaginary parts of e to the it from the complex factor.
You match coefficients?
I haven't done anything yet. So this...
Where'd you get the a from again then? A equals d minus 1?
Oh, that was a thought.
Oh, gotcha.
So just... My thought is that, hey, if I annihilate the differential equation by finding an operator which kills the inhomogeneous term, I've made it into a homogeneous problem. I already know how to solve those, right? And so this is the solution to that. And now, you're right. This is just sort of a template for the solution, right?
Yeah.
So then you plug that. So then what I tell students is like I say, so then I look at my general solution to the corresponding homogeneous problem, and I recognize there are two pieces. There's the piece which is the homogeneous solution to the original problem,
and then there's particular.
And then there's the other piece which is the particular solution. So this method, though, suggests the correct form for yp. This is not very impressive yet. What happens if instead of putting e to the t there, I put, I don't know, cosine t?
You can, well, you change your...
So I got d squared plus 1 y equals cosine t, right?
Yeah.
So we can annihilate cosine t via d squared plus 1, right?
Okay.
So I act on the differential equation by d squared plus 1. I get d squared plus 1 squared on y equal to d squared plus 1 times cosine, of course, which is 0. So let me not even write down that step. Let me just put 0 here. Try not to write it quite. So you get this is 0. That's a fourth order differential equation, right? It's the lambda, or r if you like, plus or minus I, repeated solution. So that means we get sines, we get cosines, we get t times sines, we get t times cosines. That's our general solution.
Oh, you set y equal to cosine t?
Well, so y equal to, I didn't say y equal to cosine t, I said annihilate cosine t via acting by d squared plus 1.
Okay.
So I act by d squared plus 1, operate by d squared plus 1. Take d squared plus 1 in this equation, I get this equation. Take a second order non-homogeneous, I convert to a fourth order homogeneous. But the fourth order homogeneous I can write down the general solution for.
Yeah.
C1 cosine t plus C2 sine t plus C3 t cos t
See,
plus C4 t sine t.
I'm a little lost just because, you know, if you take a differential of cosine, you never get a 0.
Oh, differentiate cosine 2 times.
Good.
Minus.
Minus cosine. Oh, gotcha. Okay.
So lo and behold, fourth order problem solution, general solution known. Of course, tilt your head squint, you can recognize.
That's 2.
Yeah, this piece right here is the homogeneous solution for the original problem, right?
Yeah.
If you plug that back in, you have yh prime prime plus yh equal to 0, right?
Mm-hmm.
Which is not a solution to the given problem, which is here, right? It is a solution to the corresponding homogeneous problem. But this piece over here is what we commonly call yp in the differential equations course, the so-called particular solution.
Yes.
And that is the correct form for yp here. See, if you make yp just a cosine t plus b sine t, as you might naively suppose from the forcing term being cosine t, it doesn't work. Because the homogeneous solution and the particular solution overlap in this case. So the method of annihilators automatically,
How do you always know when it's going to annihilate?
the method of annihilators automatically knows to put the t here,
Yeah.
which is what we need.
Mm-hmm.
And so this is general. In a sense, general.
Wait, so...
You're right. Like, how do you know?
Yeah.
How do you know what you can annihilate?
That and,
Right. How do you know?
see, when we did particular solutions, we matched coefficients.
Oh, well, this is just a right.
Quick,
Okay.
quick.
You still got to do that.
Yeah, oh, so you just skip some.
I'm just skipping. I mean, that's not interesting. We can.
Yeah.
You're right. Then you got to take this. Very good. Yeah. Plug that back in here. Equate coefficients.
Yeah.
You get like a half t sine t or something, whatever. You know, you plug it back in here. You get a equals to a half because this ends up being e to the t plus a to the t plus a to the t equals e to the t. So a is a half.
Yeah.
Great. But yeah, you can do this. And in fact, that is the principal mistake my students make when I teach this materials. They don't plug it back in and work it out. They just find the general form and they think they're done. But the thing is, method of annihilators, this part of it, it doesn't find the actual solution. It finds the form of the solution. You still have to plug it back in. Absolutely.
Okay, so, but with the method of, you can write, this can't work in every case, or can it?
Right, so the question is, L of y equals ut if there exists A such that A of g, right, equals to 0, then A L y equals to A acting on g equals to 0, right? Now that's just like, that could be generally true. However, it's only especially useful when both L and A allow the theory of factorization that we've talked about. So when L is a polynomial in the differential operator, when both L and A are elements in the polynomials generated by ddt, so this is like a fancy way of saying L and A are both polynomial in the differentiation operator. When that's the case, then AL equals to LA is, you know, itself in polynomials of the differentiation operator, right? In other words, if you can find an annihilator for your forcing function g, which is itself polynomial in the differentiation operator, then that's when this works. This is only going to work if g has to be the solution to a homogeneous constant coefficient problem for this to work. And so what is that? 1t squared, you know, t to the n. Any polynomial in t is the solution to a differential equation with constant coefficients, namely, can you give me an nth order polynomial?
Yeah.
That's the solution to y to the nth derivative equal to 0.
For this, what?
To work.
Oh.
But what else is solutions to, you know, also e to the alpha t, right?
Mm-hmm.
Or cosine beta t, or sine beta t, right? Or products or sums thereof. Sinches and coshas are also fine because they're a linear combination of exponentials. So that's when the method of undetermined coefficients works, is when the forcing term is a solution which is of the same type as the homogeneous solution. It's a function which can be obtained as a solution to a homogeneous problem. That's when the method of undetermined coefficients works. The method of annihilators explains why that is. Which is why you didn't cover it, because it's about y. But I think there's like section 6.5, so.
Yeah, I don't think we did chapter 6.
Chapter 6 is like nth order ODEs as opposed to just second order.
Yeah.
So it just kind of bumps it up a notch, you know?
Yeah, we skipped over
Now, when G is not one of these things, right? What do? Like if G is not a solution to the homogeneous problem, you use a different technique. You use what's called variation of parameters.
Oh, we did learn that.
Yeah, you did. So for sure, but you'll do n equals 2 problem.
Yeah.
But variation of parameters actually can be done for an nth order problem. I don't even test on that in my course. Like it's too much.
Yeah, I think we tested on
I will test on the second order problem, but I won't test on like the third. I have, but I typically don't test on third or higher order variation of parameter problems. Those problems involve sub-Wronskians. Let's see here. Let me get back to the paper here. I think I'm wandering.
No, I mean you were talking about that. Where is it? Okay, yeah. Find a general solution of differential equations using method of variation of parameters. G y prime prime plus 4y equals 4 secant 2t.
Mm-hmm.
GS, general solution is y of t. Y of t is equal to y h of t plus y p of t. r squared plus 4, r is equal to plus or minus 2I, alpha minus 0 beta equals 2, y1t is equal to e to the 0t cosine 2t, y2t equal to e to the 0t sine 2t. Y of t is c1 cosine 2t plus c2 sine 2t, when p of t is equal to b1 y1 plus b2 y2. There's a lot more steps.
So here's how it goes. So you know, if you're going to solve the nth order problem, right? Like this, and you know, the nth derivative a2y prime prime plus a1y prime plus a0y equals to the forcing term g. All right. Variation of parameters says the following: is like given fundamental solution set y1 through yn, form y equals to v1 y1 plus v2 y2 plus vn yn as your potential solution. So it's called variation of parameters because instead of having constants c1 through cn, you have parameters v1 through vn, which is really just another word here for functions, unknown functions, which we're going to determine from the structure of the differential equation. This is a natural generalization of the general solution for the homogeneous problem. It makes a lot of sense that you'd look at this because, of course, when we let the v1 through vn just be constants, we're back to the homogeneous solution, right?
Yeah.
So if you just add a constant to your parameters, whatever you find them, you're automatically including a homogeneous solution. All right? So that's also kind of nice.
Yeah.
So here's what's done. So you differentiate this, right? So you differentiate this, and what you get, y prime, product rule, n-fold times. You get v1 prime, y1, and I'm just going to collect these v2 prime, y2, vn prime, yn, and then plus v1 y1 prime, v2 y2 prime, vn yn prime, all right? Now, I always tell students that guessing a solution to a differential equation is a lot like, you know, trying to find a wife or a husband. You know, you have a general idea what you want, right? And then you add conditions. And you know, you can keep adding conditions as much as you like, but if you add too many, you may find that there's no solution. But at the start, we're allowed to add all the conditions that we want. So when I think about conditions, one condition that would make this easier to think about is just the assumption that all these guys work out to equal to 0. The sum of these is 0.
And you get that from where? You just trying stuff.
It's like, you know, I prefer brunettes.
Okay.
So. Or Star Wars, not Star Trek. I don't know. You pick it.
Star Wars.
Star Wars? Okay. There you go. Y prime prime then, subject to that condition, is easy to calculate.
Yeah,
Because that piece is 0 and you just got these n products, right?
Yeah.
So you've got like the v1 prime, y1 prime, vn prime, yn prime. Those first parts of the product rules.
Yeah.
And then you've got like plus v1 y1 prime prime. vn yn prime prime, right? And then you're like, no bangs. No bangs. That means this is 0. Right? I Can't stand a life partner who has bangs, who's choosing bangs as part of their haircut. Like, it's just not acceptable. I mean, you can play. So you, in this world, you get n restrictions on your partner.
So are you pretty much going until your y prime just becomes 0, like a constant?
So yeah, eventually we get to the nth derivative, right?
Yeah.
Okay, so when we get to the nth derivative, we're going to get, again, v1 prime, y1. This one, the second had the first derivative, the nth will have the n minus 1th derivative here.
Yeah.
And it'll have the nth derivative over there. Alright. And again, we're just going to assume these guys over here are equal to 0. So if you're keeping score, we have now imposed n conditions on the derivatives of v1 through vn. These are all linear equations, all right? So we can repackage all of those as a single file swooping matrix equation, where the coefficients are taken from the y's, or the derivatives of y's, or the n minus first derivative. Hey, that's a Wronski. It's the matrix of the Wronski, you'll see that. So that matrix times, you know, v1 prime, v2 prime, all the way to vn prime, right? I would say that that's equal to 0. That's not quite true. It's 0 right up until it's not. And then what goes down in that last spot? See, because I have this the last row here should be this last equation somehow. Or maybe it involves it. Let's see here. Oh, I can't, excuse me, I cannot impose that this is 0. I cannot impose that that's 0, because to say that's 0 is to force this to be 0, which that is too far. Like, it's the one thing too many. It forces you to marry yourself to the 0 solution, which isn't going to work if G is non-zero, you know. So this one here, these guys, so we're assuming that the fundamental solution set is y1 through yn, right?
Mm-hmm.
So
wait, but can't you replace everything, maybe?
Right. So like y, let's say sub j, the nth derivative is equal to g over an minus a0 over a n y j minus a1 over a, I should have written the over n. I should just written the over n out front, you know. Well, okay. Yj prime minus a n minus 1 over a n yj n minus 1th derivative.
Okay.
So So I think when I actually go back and plug that in there. Thing is, I get this mess. I get that mess for like every. This is happening for j equals 1 to n. It's a lot to write out. You see that?
Yeah.
Like this is for the service. For example, this one, it would plug up into here, right? That's just j equals to 1. And then you're going to do the same thing for 2 all the way out to n. And I think I'm thinking about this wrong. Thinking about this last step wrong. You forgive me here. Let me just take a step back and look at the nth derivative differently, okay?
I'm gonna go to my car and get a fire.
Uh-oh. So what I'm going to do is I'm going to plug in the solution into the differential equation. That's the one thing I haven't done yet.
Okay. Alright, that makes sense.
Yeah.
Be right back.
Yeah, that's the step I'm missing. I mean, I was trying to build that step into the other thing I was doing.
Mm-hmm.
It's just unnatural. Like the last step in the various parameters derivation is to plug your general solution, your ansatz, your guess for the solution, and to like plug it into the differential equation to make contact with the inhomogeneous term g. Then you got to think about, you know, as I plug this general this solution guess into the differential equation, what happens is I'm doing these differentiations, you know. Well, because of the conditions that I've placed, the n conditions I've placed on the derivatives of v, right? Basically, linear combinations of the derivatives of v against either the fundamental solution set or derivatives of the fundamental solution set, so second derivatives of the fundamental solution set and so forth. It allows me to simplify the differentiation that's present in a very peculiar way. The conditions that I placed on the parameters, that allows me to just take the derivative and when we do the product rule and the derivative falls on the v's, those terms are summing to 0. So then the sum total of that is that I can just take the derivative here. I'm gonna wait till you catch up with me because you kind of need to see what I'm doing.
Okay, so you plugged it back in. You plugged your you plugged y back in.
Yeah, I plugged the solution, the alleged solution, back into the differential equation it has to solve. And what I'm pointing out is that when we actually perform this differentiation, like do the first one, you end up with, you know, 2 n terms. N of those are summing to 0 because they're exactly these in the first derivative. And then you do the second derivative, these are going to 0 in the second derivative, and so forth and so on. So what the sum total of it is that you can cast the derivative to the function. That's the net effect of our conditions, is that this is because the first derivative term, like the derivative of v, with like the next one I haven't written for the third derivative, is that v2, I mean the next thing up the chain is v1 prime y1 prime prime plus. That's our next assumption in this tower of constraints. So I can take the derivative outside and pass it inside, because all the other terms, they add to 0 by these constraints. This one is...
So you're taking a differential operator and applying it to this?
I'm just, at the moment, I'm just plugging in this is my, you know, my solution ansatz, you know, this is that's just German for gas, or gas. I'm assuming that y1 through yn are solutions.
Yeah.
To the homogeneous problem. It's like this last piece here,
Yeah.
Product rule gives me, like I wrote up here, it gives me this and that. I'm assuming that piece is 0, so I just have that, which amounts to erasing this prime and just writing it on those. Okay. 1 sec.
So, could you, are you gonna like,
And I think I actually still have,
are you gonna rewrite it?
and I missed one thing over here. There's also, in this top term, there's also an v1 prime plus v1 prime y1 plus vn prime yn. I believe. Because I don't get to I do have that. That's not right.
Okay, so when we learned it, we set our homogeneous solution to like a more standard homogeneous solution. So like for us it was C1 cosine t plus C2 sine t, where the e's, the alphas were 0, or the betas, not for which one. But our particular solution was b1 y1 plus b2 y2. And how we got rid of it is let me see. I'm trying to go backwards. Sorry. Essentially, setting up a system of equations where you get v1 prime equal to something that's integratable. And so you integrate it and you get v1 equal to a function. And then you plug v1 back in, and now you have a particular solution.
Right. So
that's what I was trying to say here, is that are you going to take out a v1 to vn?
I'm going to solve that system of equations.
Yeah.
For this problem, it's going to be n equations and n unknowns.
Yeah.
I'm going to solve it with matrix multiplication.
Okay.
I'm actually going to be able to write the general solution down by Kramer's rule.
Okay.
So it circumvents the hand-to-hand combat with solving equations like you were taught. Which is encapsulated by equations 9 and 10 in that section of the text for what it's worth. But anyway.
Okay, so back to this part.
Yeah, and I'm sorry, I need to write out more and I'm just too lazy at the moment, but like you can see.
So I see what's happening.
So you've got like an.
You're just getting zeros.
See this?
Yep.
An, these terms.
Yeah.
So you could factor out the v1. You've got an, y1.
So isn't there supposed to be a prime there though?
That's n primes.
No. I'm talking on the v. Oh, you put it down low.
So you've got the v without the prime, and if you factor out, so you get a v1 here.
Yeah.
And here.
Yeah, that's what I was saying. Yeah. You factor it out.
Factor it out, and you have exactly this, but with 1.
Yeah.
Right? So that adds to 0.
Mm-hmm.
And then, like, in fact, all of these terms go to 0, except for the, except for, if I remember right, and it's debatable. So I feel like I'm butchering something here, but you just get.
Shouldn't those okay, so you added an on the bottom there. Shouldn't that be v1 prime y1 n minus 1?
But I know that that's 0.
You know that.
Because
No, that's the a nth, and whenever you said you couldn't go to 0 on the a to the nth term. On the last derivative.
Oh, on the last derivative, I don't have that one.
Yeah. You said that.
Oh, okay. So that you're saying I just left with.
Yeah, it should be n minus 1 prime. Yeah.
Oh, okay. So that then gives me. So my last equation. Perfect. Thank you. Perfect. So I have this equals to that.
Yeah.
Everything else works out to 0. And so that gives me this last thing, and over here not 0, but g over a n. That's what was bothering me. It looked complicated before, but I know it's something rather simple when you actually work out the beats, because all this stuff vanishes to 0 because they're solutions.
Yeah.
Except for that one term. But look at what you have then.
You have a matrix multiplication where you get zeros in an answer.
Right, well,
but not only an answer, you get the answer divided by the an term, which is
the homogeneous, the forcing function, whatever it is.
So this is a particular solution, right?
Yeah. Well, this is the hopefully it's the general solution.
Okay.
I mean, so that's the question: is does this work as a general solution? And I think the answer is yes, because. So I guess the biggest question at the moment is like, can this matrix, can we actually solve for the v1 through vn? Well, I would point out to you that this is the Wronskian. Well, this isn't the Wronskian. This is the matrix, the determinant of which is the Wronskian of y1 through in. Remember, we've assumed that y1 through in is a fundamental solution set.
Yeah.
Therefore, this is an invertible matrix. So if I just call this thing, you know,
Well, how can we assume that because it's square? But just because it's square doesn't mean it's invertible.
but Zarinsky is that the
Determinant is non-zero, yeah.
determinant non-zero, which means that this is invertible.
Yeah, but how do you get determinant non-zero from just saying the
Let's
solution
assume that
set?
this is a fundamental solution set, which means n linearly independent solutions to the corresponding homogeneous problem.
Oh, if there was zero, they couldn't be linear independent. Okay.
So like it is assumed from the outset that we have a fundamental solution set, which means that this is an invertible matrix.
Yeah.
Which means that I can solve, if I call this, and so it's helpful to use notation, let's call this x, call this dv dt,
Okay.
and call this, you know, f vector or something. So what you've got is you've got x dv dt equal to f, which implies that
X is at prime.
right, dv dt equals to the inverse of x times f, which then you can integrate. The v is the integral of x inverse of f dt. So, therefore, the general solution, x,
Yeah, that's what we do here too. We integrate.
right, it's x times v, which is x times the integral of x inverse f dt. And that is the formula for variation. This is the variation of parameters formula for the nth order problem.
Oh, this is different. Wait, x arrows equal to x bar times b bar is its b.
So this
Sorry, arrow. I know it's a vector, but
yeah, let me see here. Getting too hard ahead of myself.
wait. So how do you know x
Yeah,
bar?
yeah, yeah.
Oh yeah. How do you know x bar is
that way? I shouldn't write it that way.
Is
So this is
b is
this is my you know here. Sorry, I'm thinking of systems. This is the parameters that we're trying to find, right? And then you take those, and your solution is, like we said, d1, y1, you know. Just to be more specific, like take the, if you had the y prime prime plus y equals to secant 2t problem.
Yeah.
Alright, so this has y1 equal to cosine t, y2 equal to sine t.
Yeah.
Right? So this v should be the integral of x. What is x? X is cos t sine t minus sine t cos t.
No, that just gives you determinant one though.
The determinant is right. So x inverse is what?
You flip A and B, keep B, C the same.
I think you have to flip the sign.
Oh yeah.
That corresponds to the fact that this is rotation by t.
Yeah.
This is rotation by minus t. So you got yourself a cosine t minus sine t, cosine t.
Times F.
F, now F, remember, is this guy.
Yeah.
For us, a sub n is 1. So that's just 0.
And 1.
And, well, not 1, here's secant 2t.
Oh. Yeah.
And so,
0 plus.
right, yeah, minus sine t,
Yeah.
sec 2t,
Yeah. And then the other one.
yeah, cos t, sec 2t, dt. And I'm sure those are integrals that you did.
We did the integral. Did you do the integral of tan? Somehow. Cosine
Did you have
t.
secant t for this actually? Secant 2t? You had secant t.
4 y prime prime plus 4y equals 4 secant 2t.
4, okay, so 4y. If you put a 4 here, secant 2t becomes easier.
Yeah.
With just a 1 here, the thing to make this reasonable, and I mean, this is not unreasonable, it's just a pain to do the integration. Just erase the 2 to make this a, like, not onerous problem.
Yeah.
It's not, just the integration's messy if you put a 2 there. And then, of course, like, cosine secant is 1.
The integral of it?
And sine secant is tangent.
Yeah, I knew that.
So that's what you're left with, integrating minus tangent t, and integrating 1.
So you get t.
Yeah, you like I'll
and then you get a nasty
minus the natural log
of secant t
of cosine t. And if I erase the plus, there we go.
You sure it's cosine t? I got secant t on my paper.
If you put a minus out front, it becomes secant.
If you put a minus out front, yeah, that's what it.
Yeah, minus log secant. That's the same as log cosine.
I don't know that.
But well, it's just, you know, log of x to the minus 1 is minus log x. It's just that. So if you have like log of secant, that's log of 1 over cosine.
Yeah.
Which is minus log cosine. It's just this.
It's gotcha.
So yeah, so we get. So the answer is like, you know, log cosine times cosine log cosine plus t sine is the particular solution. And of course, if you just add constants, right? If you add arbitrary constants up in here, that automatically picks up the homogeneous solution that you need for your general solution.
Yeah.
But variation of parameters is a general technique because this Wronskian, I mean, the assumption that there exists a fundamental solution set makes this an invertible matrix, which means that we can solve for the derivative of the, you know, the parameters and integrate. But, you know, you don't want to make students do this past n equals to 2 because it basically amounts to inverting a 3×3 matrix of functions, which you can circumvent by using Kramer's rule. You can always write, you can like solve.
I wonder if everybody took linear in my differential.
You can solve this for the jth derivative, the like dvj. You know, you can solve for dvj.
Well, it's always going to be a square matrix, so of course it's not going to be horrible, but it could be horrible.
Well, the thing is, you can use Kramer's rule. You can take the quotient of like the determinant over the determinant of x. You know.
This is somewhere in my notes. I know.
So like the Kramer's rule, you take the jth column and you swap it out with f. You know. And so when you actually look at that's why I was talking about sub-Wronskians.
Yeah.
Because when you actually take this x and you swap out a column, you have some matrix, determinant of a matrix, which involves n-1 things. So it's got like all but the jth fundamental solution forming a Wronskian that's called a sub-Wronskian. Anyway, this is in your book, but it's in chapter 6.
You do not own that book anymore.
Ooh, you should get yourself a copy.
Yeah, I did the.
Well, if you have a PDF of it, that probably would suffice, I guess. But
yeah, if there's a PDF of it out, but I had the Pearson text so in my math lab, so you know the book was kind of pointless to buy because I needed the access code for the class.
Mm-hmm. I am fond of the 4th or the 3rd edition of this book. That's what I like. It's got like 7 or 8 editions now, but I think the 3rd or the 4th edition with the boundary value problems, that's the one to own. It served me well. Like the first time I taught differential equations, I just took 3 weeks in the summer and just solved the lion's share of the homework in the book. Just solved it, you know. Oof. And then, so then when I go to teach the course, I'm like, I'm ready. I think that's the best way to, one of the best ways to teach, at least like if you don't have like a lot of, I mean, maybe you had a course from a fantastic teacher, you already like know, oh, I want to copy his course, right?
Mm-hmm.
But I didn't quite have that feeling myself for differential equations, so I felt like I need to like really meditate on the book and try to come to my own understanding of what this is. Nagel, Saff, and Snyder is how I did it. Anyway, yeah, this is various parameters. Now, the question is,
Why is it called that? Is that because we're switching out the y?
yeah, because you're varying these parameters to construct the
Oh,
general
because
solution.
you keep setting them equal to 0. Got it.
Yeah, and then, I mean, this, it just so happened, like, on the surface of things, like, why are you setting this equal to 0? Why are you setting that equal to 0? It's very, like, what's going on there? How do you, but then if you think about,
Yeah,
it actually makes complete and total sense if you have your eye on the prize, which is what you're given.
the matrix.
Linear independence of the fundamental solution set.
Yeah.
That is most elegantly described by the invertibility of that matrix, or the determinant of the vanishing.
No, yeah, I totally got why you're putting it to 0, because I was like,
Yep.
you just want the one answer.
So that's the invertibility. is
What
given.
what happens if you have multiple answers? Like, this is not 0. Does it just become ugly?
What do you mean that's?
Yeah, like if we don't set all of them to 0, like that's not a parameter that we set them to.
Well,
Because, like, you know, we set it equal to 0 because we said so. We didn't have to.
hmm.
I'm saying this because if we wanted to do this in a different algebra,
I mean,
we maybe not set it to 0, but maybe set it to a 0 divisor.
well,
Like, maybe that would be easier to do instead of 0.
but just trying to think about what that would mean if those were. I mean, there is tremendous freedom in what can be shifted around in these formulas, because like all of this stuff going on is subject to that differential equation,
Yeah.
but not that. It's subject to all those things being equal to 0 for these y1 through yn, right? So like you can, there are certain linear dependencies that can be exploited. Hypothetical. If I was working with the differential equation y prime 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 plus y prime 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 plus y prime prime plus y prime,
Plus y.
yeah, plus y equal to 0, right? And I had a formula which involved y prime prime plus y prime. I could swap that out for minus y prime 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 minus y prime 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 prime. For the fundamental solution set part of the formula.
You get 0.
Those are equal. So, you know, what I'm trying to say is, I think you're possibly right that we could put something other than 0 there as conditions. And, you know, I don't know what that would mean, but you're right that it wouldn't spoil the derivation because it's really the uniqueness. It's really the uniqueness of the coefficient matrix which drives solving for the v primes, which then you can integrate. I mean, whatever when you solve the v primes and you look at the integral on the other side, that is what you want to say. I'm gonna choose that for v because when I plug it back in, it's gonna solve all this mess and it's gonna work. I think you're right though. I think you could put something other than 0 there. But I don't know what it would do. I don't know what it would do. Oh, you know what it would do? It would complicate this derivation immensely. Because instead of having 0 here, like if I made it 1, I'd have a 1 here. Would that be a problem? But maybe it wouldn't be much of a problem, because when I differentiate the next thing, 1 prime is still 0. It'd be more problematic, like maybe putting constants there is not like a big modification of the argument. But if I put like e to the t.
That wouldn't be that big of a complication either, in my opinion, because you're just keeping e to the t.
Yeah, but
it'd be something ugly. Yeah, but something ugly.
But then that will have the follow consequence of not making all of this stuff vanish down at the bottom.
Because, because e prime, because you gotta take the product up,
you know, Udrick, I really don't know. I have not thought too hard about what if you chose something other than 0.
I'm saying choose something other than 0 that might work in a different algebra. That's my thought process. Something that maybe like before we couldn't differentiate, but maybe if we made it a 0 divisor, everything would still annihilate without having to use 0. Man, because for some reason 0 won't work in that algebra.
Yeah.
I can't think of one off the top of my head, but that's kind of my...
I think though, if we have an nth order AODE, and we have a fundamental solution set, right? As we defined, then I think essentially this calculation still goes through when the derivatives here are replaced with algebra derivatives. So I guess that's comforting. But actually, I don't know how I got off on this topic. Oh, I'm sorry, I'm chasing a giant rabbit here because what I was trying to talk to you about was solving the homogeneous problem today, right?
We solved the homogeneous problem.
Right, but we need to look at more. I mean, we want to understand it in about 3 different ways.
Okay.
And so one of the things that, so you know, working this out from the base up, the first question is, how does factorization of polynomials over an algebra actually work? You know, like what are the rules for factoring polynomials with coefficients from an algebra? Right? Oh, sorry, I don't know why I got us into that. I did want to talk to you about the method of annihilators because I think that just helps review. I think it helps review the idea of operator, like operator-based solutions to differential equations. And it's just also something that you probably didn't see in your course, right?
No.
So I think it's maybe helpful.
Okay.
So let's look at Theorem 5.1, see if we can appreciate it for what it is. Theorem 5.1, it says, suppose that d equals d d z is the operator.